All right, welcome back. Math 1910. We're still in chapter 1. We're into section 4. We're going to go over continuity and one-sided limits. All right, so far we've been learning about limits and understanding when limits exist. All right, and remembering that the left-hand side has to equal the right-hand side. We learned some techniques about factoring, being able to simplify in case there was a whole, or if we had to rationalize the numerator, denominator, multiplying by the conjugate, those sort of things. We looked at the squeeze theorem. All right, we're going to kind of carry those over into here, and we're going to talk about continuity and how those apply to continuity. So we want to be able to determine continuity, okay, on an open interval. Remember, an open interval is where we do not include the endpoints on that interval. All right, we want to determine one-sided limits. So we're talking about approaching, x from the left or approaching x from the right, and talk about how the continuity can affect that. We're going to talk about different properties of continuity, and we want to understand, very important, the intermediate value theorem as we go through all this. Okay, so for the most part, the term continuity should make sense to you. We're talking about something that is continuous. So a function is continuous, which means without interruption. Okay, so at every specific point on the interval, everything exists, all right? So it's unbroken. There's no holes, there's no gaps, there's no jump discontinuities or anything like that as we're going through and taking a look and analyzing on the interval. Okay, so let's talk about continuity at a point. Okay, so we want to look at this. There's three different graphs we have going on here, and all are about the limit as x is approaching c, either if we're coming from point A or if we're coming from point B. So we want to imply how the graph could be continuous or discontinuous at a point. So we want to see, is it completely uninterrupted there? If we look at the very first graph on the far left-hand side, we can see that f of c is not defined, right? There's a hole in the graph there. So it's continuous from A to C and from C to B, but not from A to C because there's a hole in the graph. Okay, it's broken, so the function is not continuous at C. Next, if we look at the middle example, since the limit does not exist, notice, how do we know the limit doesn't exist? Because the left-hand side and the right-hand side do not agree. They're not going to the same value. So even though the limit does not exist, okay, and that way we can conclude that the function is not continuous, okay? So first, okay, we're just going to revisit here. So looking at the first graph, if the value of f of c is not defined, it's not continuous. If the limit does not exist, it's not continuous, okay? And then we got to look at the last piece, all right? F of c does exist, right? The value of c exists. That's where the black dot is. However, the limit does not exist because the c drops. So the problem is the limit does not exist or does not equal the value. I'm sorry, I misspoke. I said the limit doesn't exist. The limit does exist. However, the limit doesn't equal the value. Therefore, it is not continuous. Okay, so that's understanding the three conditions for when the function is not continuous. All right, it's not defined, it has a jump discontinuity, or the limit doesn't equal the value. So those are the three cases that you're going to be looking for when we talk about continuity and seeing if it exists or not, or if it's continuous. Okay, so it's very important that you write down those three rules that we take a look at here. All right, so Rule 1, the function's not defined at x equals c, so that was the first graph that we looked at. Rule 2, the limit of f of x does not exist at x equals c, so we saw that, right? The left hand and the right hand limit didn't agree. And then thirdly, the limit of f of x exists at x equals c, but it's not equal to f of c. So the limit doesn't equal the value. All three of those conditions tell us the function is not continuous. Okay? So as long as all three of those conditions are false, the function will be continuous. Okay? So we need to apply that as we do this. And here's writing it more formal, okay? F of c is defined. This is how we define if it's continuous, right? This is formally writing it. F of c is defined. The limit of f of x exists, okay? And the limit equals the value of the function evaluated at c. So this is how we define that it's continuous. All right, so on your homework assignment, have these three things written down. And you are going to go through all three of these checks to see if a function is continuous or not. So you might have to analyze it graphically or analytically to solve all of these. Okay, so the definition states below, a function is continuous on an open interval from a to b. Remember, we're not including the values at a and b. When the function is continuous at each point in the interval. A function that is continuous on the entire real number line is everywhere continuous. Okay, so the real number line, negative infinity to positive infinity, so if it's continuous on there, it will always be continuous. Okay, so if we look at an open interval that contains the real number c, okay, we can, if the function f is defined on I except at c, right, so our function is not defined, okay, this is how we're going to define different types of continuity here. So if that function, so if you think back at the first three graphs we look at, we're talking about the first one there, and f is not continuous at c, it's said to have a discontinuity at c, right? So when we start talking about discontinuity, there's two types of discontinuities. There's a removable and a non-removable discontinuity, okay? So a discontinuity at c is called removable if f can be made continuous by appropriately defining a value for c. So we could evaluate and say that f of c is the limit. Okay, so if we can define it that way, we can say that it's called a removable point of discontinuity. So let's take a look at this. All right, these are the same three graphs that we talked about before. So what could happen here? Well, if we look at figure A, that's a removable point of discontinuity, right? Because we could actually define a value at c, and if we define a value at c that equals the limit, then the function would be continuous. Okay? Look at B. Remember, that's our jump discontinuity. There is nothing I can define for c that will make it continuous because the left-hand limit and the right-hand limit have such a gap between them that no matter what I define it as, all right, the limit will never equal the value there. So that's called non-removable discontinuity. Okay? And then we look at the last one, right? We defined a value at c, but the value is not equal to the limit, all right? But it is still considered a removable discontinuity. So there's the three we're going to approach. So let's do these examples here, all right? So we're going to do example A, B, C, and D, and we're going to talk about the continuity of each function as we go through this, okay? So this is part A. So we can conclude that f is continuous everywhere. So this is the first graph, okay? This is f of x equals 1 over x. Well, where are we going to have any discontinuity? Well, it's 1 over x, so when x is 0, right? We have discontinuity. And what type of discontinuity is that? It's a non-removable. Why? Because there's an asymptote there. There's not a specific value that I can define for x where the limit would equal the value, because if we look on the left-hand side of the graph, all right, it's going to negative infinity, and the right-hand side of the graph is going to positive infinity as we approach x equals 0. So there's no way to make this function continuous. So I guess when you're thinking about these, in order to determine, hey, is it removable or non-removable, really just ask yourself a question. Is there a value that I can place for x that makes it a continuous function? If not, it's a non-removable point. It kind of just comes down to being that basic. All right, so let's look at example B here. All right, the domain's all real numbers except for x equals 1. All right, so the function for this one was x squared minus 1 all over x minus 1, right? It's continuous everywhere except for 1, because what happens when we substitute 1 in, we get division by 0, all right? This is like what we've done in the past few lectures where we have a hole in the function, all right? So we can see that the hole appears at 1. It's not an asymptote, all right, but it's just a hole at 1. What we could do is define a value at 1 to be 2. When we do that, we could make it continuous. So when we have just a hole in the graph, this is called a removable discontinuity. So you're going to have multiple homework problems where you got to distinguish between removable and non-removable discontinuity. Okay? So you should be able to kind of understand that, right? I could make a point here at 1 and make it so the function is continuous. All right, moving on here. Let's go ahead and take a look at the next example here. All right, so this is not number C, but this is part C, okay, of our example here. So here we have a piecewise function. So remember, it's a piecewise function, okay? Remember, it's a function that's made into separate pieces, for lack of a better term, I guess, on that. All right, so anytime x is less than or equal to 0, we have the graph of x plus 1, and then as long as we're greater than 0, we're going to roll with x squared plus 1, okay? So we have to look at a couple different things here. When we have a piecewise function, all right, so remember, we have to check, is the function, continuous the whole way, which means that what's the point in question here? The point in question is going to be as x approaches 0, right? Because that's where we're changing functions. So we have to make sure that the value exists at 0, that the limit exists at 0, and the limit and the value are the same. Okay, so, how do we do this? Well, since we have x is less than or equal to 0, we know the value does exist for this function. Okay, if we plug in x equals 0, we evaluate it in the x plus 1 piecewise piece. So 0 plus 1 is 1. So there is a value at x equals 0. And then if we look at the limit graphically, so if we're looking from all the negative values up to x equals 0, so if we're approaching it from left to right, as we're approaching x equals 0, the limit appears to be 1. And then on the opposite side, if we're coming in from the right-hand side, we're coming down that parabola, and we're getting closer and closer to when x equals 0, the limit is also 1. So the limit does exist because the left-hand side and the right-hand side are equal to each other, all right? And the limit equals the value. So there's a defined value, there is a limit, and the limit equals the defined value. So in this case, we can conclude that this function is a continuous function, okay, on the entire real number line. Okay, let's look at another example here where we're talking about y equals sine of x. Well, we know, just offhand, right? Sine is continuous for ever and ever, right? Unless we do some different things and create some asymptotes, it's going to oscillate forever. So there's really nothing that we can do to this sine graph. At each value on sine, no matter where we pick. So if we pick pi over 2, right? We can say we know that sine of pi over 2 is 1. And we know that the left hand and the right hand limit as x approaches pi over 2 will be 1. So the limit exists, the value exists, and since the value equals the limit, we know the function's continuous. And I can do this at every single part of this sine wave. So we know that sine is continuous, all right, all across its domain. Okay, let's start looking at one-sided limits here. Okay, one-sided limits mean we're either coming from the left-hand side or coming from the right-hand side only. When I say coming from the left-hand side, that means we are traversing down the graph from left to right as we approach the specific x value. Okay, if we're coming from the right-hand side, we're coming from right to left, okay, on the function, and we're looking as the function gets closer and closer and closer to the defined x value. Okay, the defined x value is what x is approaching, so whatever c is. Okay, so we denote it differently. So if you look at the bottom left-hand side here, we have the limit of f of x equals, the limit of f of x as x approaches c with that little superscript plus sign. That means we are approaching from the right. To approach from the left, instead of a plus sign, we would have a minus sign. So when that superscript on the c is a plus, we approach from the right. When the superscript above the c is a negative, we approach from the left. And we are only looking. So a limit or a function could have a left-hand limit, it could have a right-hand limit, but it doesn't mean that it has a limit if the left-hand limit don't equal the right-hand limit. So a function can have two different limits, a left hand and a right hand, but it doesn't mean that it has a limit if the left hand and the right hand don't equal each other. Okay? So this is what I was talking about on the last slide as well. This is approaching from the left. So notice now there's the superscript of a -1. So we have the limit of f of x as x approaches c. I read it, instead of saying negative, you read it, the limit of f of x as x approaches c from the left. So that negative sign means we change the verbiage to from the left, or the left-hand limit. Okay? So let's take a look at how useful a one-sided limit can be. All right, so let's take a look at this function here. We're taking a look at the limit as the limit of the nth root of x as x approaches 0 from the right. Well, why would we not want to approach 0 from the left here? Well, that's going to give us negative square roots, or negative nth roots. So the functions may or may not exist. So it's not going to hold true necessarily if we have a limit there. But if we have the nth root, okay, and as we approach from the right, the value becomes 0. Okay, so this is how we kind of avoid having imaginary numbers or things like that. So let's do an example here. We've got a one-sided limit. We want to find the limit of f of x equals the square root of 4 minus x squared as x approaches -2 from the right. It's important too, because if we approach -2 from the left, we're not going to get any values, right? If I substitute in a -3, -3 squared is going to give us 9. We're going to have 4 minus 9 and get the square root of -5 and get an imaginary number. So that's why we have to stay within strict confines, okay, of the domain of the function here. All right, so we can only approach this function, we can only approach -2 from the right, not from the left, because it won't be defined. So looking at the graph of this, right, you can see now why we can only approach -2 from the right. There's nothing that exists from the left. So this is why we only have a one-sided limit. So as we approach -2 from the right-hand side, and we look at this graphically, and it's okay for you guys to put this in your calculator, graph it, right? We have a semicircle going on here. So if we are a particle on this function, and we're going down this function, and we're moving from right to left because we're approaching from the right-hand side, right? We're approaching -2 to the plus, which means we're approaching from the right. So if we're a little particle going down this function, as we get closer and closer and closer, and we are on the function to -2, the limit is 0. Remember, the limit's the y value. So the y value is 0. So we can say that the limit has a right-handed limit, but there is no left-handed limit. So there is not a limit for this function because the left-hand limit and the right-hand limit are not the same. There is no left-hand limit because we cannot move along this function from left to right and approach -2. We could move along this function and approach +2 from the left, okay, but we cannot approach -2 from the left for this function. All right, let's take a look at the greatest integer function. I don't know if you guys, remember doing this in Algebra 2 or anything along those lines, but it's the double bracket. So what does that really mean when we have the greatest integer function? You might have heard it called like the step function too. So what happens is it goes to the greatest integer. So when we take a look at the graph of this function, the greatest integer of anything, 2.1, 2.2, 2.3, 2.4, all the way up to 2.9 will always round down to 2. So the greatest integer of 2.1 is 2. The greatest integer of 2.2 is 2. The greatest integer of 2.5 is 2. The greatest integer of 2.8 is 2. The greatest integer of 2.9 is 2. Then when we get to 3, everything will go to 3. So the greatest integer of 3.1 is 3. The greatest integer of 3.3 is 3. The greatest integer of 3.9 is 3. So we call this kind of the step function, okay? And then we got to go the other way too. So the greatest integer of -2.5 is -3. -2.1 is -3. So it always goes down to the smallest integer. Okay, so negative 2.1's greatest integer is negative 3. Okay, until we get to that next point. So the greatest integer for like negative 1.8, right, is going to be negative 2, and so on and so forth. So that's the greatest integer function. I'm going to stop it just for a second because I want you to grab your calculator so that I can show you how to go through and graph this. I'm going to step back 1 second on the slide here. Alright, so hopefully you got your calculator now, because I want you to be able to graph the greatest integer. Because the greatest integer is going to only produce either a left-hand limit or a right-hand limit for us, because the left-hand limit and the right-hand limit are not going to equal each other with the greatest integer function. So if you don't know how to put this in, I'm going to walk you through it. I'm on a TI-84 Plus. Alright, so you're going to hit y equals on your calculator, and then you're going to hit the math button. Okay, so when you go math, and you're going to go over to number, and then you're going to go down to number 5 that says INTs for integer. Okay, and inside that you're going to hit X, close your parentheses, and then you're going to hit zoom 6, which puts it in a standard form. You're going to get the greatest integer function. That is a step function. So it's going to stay at a constant integer. Okay, it'll stay at a constant integer for that entire time, and then it steps up at the next X value. And it's going to stay at the same value until it gets to the next X value, and then it's going to step up. And then step up. Alright, so take a look at the difference ones. So change your y equals to integer like x minus 4 in your greatest integer. Alright, hit zoom 6. So you can see, what does it do? It just shifts the step function over. And then if we did x plus 4, it would shift it to the left. So just so you guys know, the same rules apply for, you know, parent functions and being able to shift them left, right, up, down, and do all those different things. But I want you to make sure that you know how to graph the greatest integer function, because they're going to have homework problems where you have to understand how to find the limit, you know, as x approaches a specific value on the greatest integer function. So make sure that you know how to put it in your calculator when you guys do that. Okay? Email me if you got any questions on that as well. Okay? So this is called the existence of a limit. You've heard me already talk about this as I've gone through some of the examples, okay? So, for a true limit to exist of a function, the left-hand limit and the right-hand limit have to be the same thing. And that's really what this is defining, the existence of a limit, okay? So it says, let f be a function and let c and l be real numbers. It says the limit of f of x as x approaches c is l if and only if the left-hand limit, right, as x approaches c from the left, and the right-hand limit as x approaches c from the right, both equal L. So that's the only way to tell if a true limit exists, okay, because the left-hand limit and the right-hand limit are going to the same value. If the left-hand limit does not agree with the right-hand limit, the limit does not exist. The left-hand limit might exist, and the right-hand limit might exist, but the limit doesn't exist because the left hand and the right hand are not equal. So just make sure that you understand that piece as we go through this. Okay, so it's really helping us understand what's going on and about continuity when we're talking about closed interval. Okay, so a function is continuous on a closed interval when the continuous on the interior of the interval exhibits one-sided at the endpoints. Okay, so if we take a look at the next definition here, this is called definition of continuity on a closed interval. Okay, so this is how we can define when f is continuous. Okay, so as long as it's continuous on the open interval a to b, and the limit as x approaches a from the right, and the limit as x approaches b from the left exist, okay? So as long as there's a left-hand limit and a right-hand limit. Notice how the dots are closed there too, signifying that they exist. Then we can say the function is continuous from the right at A and continuous from the left at B. So that's going to tell us the function is actually continuous on the closed interval A to B. So let's recap that. So if a function is continuous on the open interval a to b, and the limit at x equals a exists from the right, and the limit as x approaches b from the left exists, as long as those two endpoint values exist, or the endpoint limits exist, then the function is said to be continuous on the closed interval. Okay, so we'll take a look at some examples here. Let's see if we can work through this one. We want to talk about the continuity of f of x equals the square root of 1 minus x squared. So automatically in my head when I'm approaching this problem, I'm thinking, all right, what value is this going to start getting shaky at? Well, if we plug in 1 for x, right, I get 1 minus 1, which gives me 0. So I know that works. What happens if x is 2? Well, then I start getting a negative square root. If x is negative 2, I'm going to get a negative square root. So I already kind of know, where I'm looking at on the graph of this function. Okay? So we know the domain of this function has to be between -1 and 1, and it's on a closed interval, right? I can substitute in the value of -1 and get back a value, and I can substitute in the value of 1 and get back a value. That value is 0, okay? But if we notice that all points on that open interval, -1 to 1, the continuity of f follows the two theorems from before, right? It's continuous on the right because we are going to approach the endpoint as x approaches -1 from the right-hand side. We get 0, right? F of -1 is 0. And then if we approach 1, okay, from the left-hand side, the value exists, it's 1. So does that make sense so far? The left-hand limit and the left-hand limit and the right-hand limit, the endpoints, the limit exists, okay, using the left and right-hand limit. So it's continuous from the right and it's continuous from the left all the way to -1 and 1. So we can conclude that since the limit does exist on each endpoint being x equals -1 and x equals 1, the limit does exist. It's 0 for both of them. It doesn't have to be the same. It just has to exist on the interval. We can conclude that this function is continuous on the closed interval from -1 to 1, okay? Because we evaluated the limits at the endpoints, okay? So as long as we're continuous on the endpoint, or we have limits on the endpoints, and it's between our interval from -1 to 1, we are continuous on the closed interval. Okay, so there's kind of how you go through those. Let's take a look at properties of continuity. These are all the same, sort of properties that we go through. We got a scalar, so we're going to take, some value b times a function. We have a sum or difference. We have a product, and we have a quotient. Okay, so what's that really say? If b is a real number and f and g are continuous at x equals c, then these functions below are also going to be continuous, right? Any sort of scalar, sum or difference, quotient, or product of those functions, as long as they're continuous and we're blending them with continuous functions, they will be continuous as well. Okay? So, if we just want to summarize functions that we've studied, so far, and if we come across these, and this is going to be kind of your approach, right? If we have a polynomial, a radical, or a rational, or a trig function, okay, we can combine all these theorems and classify, their continuity. So let's take a look here. If we take a look at each function that are continuous in each and every point in its domain. So f of x equals x plus sine x. Okay, we know that that's just a sum, right? I'm just going through the continuity. We know that x itself is always continuous. It's just a straight line. There's no holes, no gaps, or anything. We know sine, standing alone, is what? Continuous for, negative infinity to positive infinity. So if we take a continuous function x plus a continuous function sine x, and we put them together, that function will also be continuous, okay? We're just applying these properties right here. All right, it's property number 2, that's our sum, okay? If we have f of x equals 3 times tangent of x, well, we know 3 is continuous, right? It's just a horizontal line, 3. We know tangent, okay, is it continuous at every single possible point? You got to be careful there. When does tangent become discontinuous? All right, so will that function work, and is that always continuous? Tangent is not a continuous function because we have what? Sine over cosine. So every time cosine goes to 0, right, at pi over 2 and 3 pi over 2, tangent is not continuous, okay? So we got to be careful there. That function is not going to be continuous, right? If we look at x squared plus 1 divided by cosine of x, we're going to have issues when cosine goes to 0, okay? So we know right away that function is not going to be continuous as well. Sorry, I skipped ahead there for a sec. All right, so we can talk about the continuity of different composite functions. So we have sine of 3x, we have f of x equals square root of x squared plus 1, and we got tangent of 1 over x. All those different things that we're going to apply that can make these, continuous or discontinuous. So sine, regardless of what we do with that 3, all right, will always be continuous. I can put anything in for x because sine of x is just 0. Sine is still continuous. All right, so regardless of if I put a scalar in there, sine will always be continuous. Let's look at the middle function here. We have f of x equals the square root of x squared plus 1. Is there any value in there that I can really put that's going to make this so it's discontinuous? Even if I put negative 1 in there, the function will always, we won't have any imaginaries. Even if I put 0, it'll be at 1, right? All positives are going to work and all negatives are going to work because we're squaring the function. So that function is continuous. All right, how about tangent of like 1 over something? Is tangent ever going to be continuous? No. Okay, so tangent is going to have discontinuity. All right, so taking a look, moving forward, we got Theorem 1.2. We're talking about continuity of a composite function. So these are what we just looked at, okay? If g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x, okay, remember that terminology, f of g of x, all right, is a continuous at c as well. Okay, so if we have two continuous functions and we make them a composite function, by putting one function inside of the other, it will also be continuous at that same point. Okay, so we want to take a look and describe the intervals on which this function is continuous. All right, so we know tangent is sine over cosine, and we know that tangent is always going to be discontinuous when cosine goes to 0. So at pi over 2, negative pi over 2, 3 pi over 2, all those different values. So, but in between there, okay, so if we take a look, at tangent from negative pi over 2 to positive pi over 2, tangent is continuous, but it's not continuous at pi over 2 or negative pi over 2, okay? And we're going to go through each one of these here. All right, so we should know, all right, it's undefined at these points. Pi over 2 plus n pi over 2, okay? We did all of that last semester in pre-calc 2. But at all other points is continuous. So this is where we know it's not continuous because that's where cosine goes to 0 and tangent is sine over cosine. That gives us, division by 0, which makes it discontinuous. So that's where our asymptotes are. Okay? So if we graph tangent, all right, we can see that it's continuous on, from negative pi over 2 to pi over 2, from pi over 2 to 3 pi over 2, but not, it's continuous on the open intervals, but not on the closed intervals as we go through that one. Okay? Let's look at the next one that was on there. Okay, so if we graph this one, we have y equals 1 over x. It's continuous at x equals 0. And then we have sine of that function. So our composite function here, we have y equals 1 over x. So the first function we need to look at is the 1 over x. 1 over x is continuous everywhere except for at x equals 0. There's a point of discontinuity. And then what happens here? We stick that into sine of x. So sine of 1 over x is continuous at all real values except for at x equals 0. Okay? Since g of x didn't exist at x equals 0, sine of 1 over x will not exist there either. Okay, so this function is continuous from negative infinity to 0 and from 0 to infinity, but is not continuous at 0 because 1 over x is not continuous at 0. Okay? So look at the last one here. If we apply the squeeze theorem here, we have h of sine of 1 over x, okay? And then we have the absolute value of x, all right? And we have our other function there. So we can, by the squeeze theorem, okay, we can, remember that's the one where if we have a function, we have two functions, right? And the third function we're looking for is in between those two functions. we can conclude that it will also have the same limit as well. Okay, so what we really need to understand here, it's very similar to the one we did before, but this one is dampened. Okay, this one's dampened because we have the x in front of the sign of 1 over x. So that's going to make the graph look slightly different as we go through this. Okay, so what we can do is conclude here that, but remember, x, sine of 1 over x, as long as that one has a limit or is continuous right there, it's continuous everywhere except for 0. And then the other graph is continuous except for 0 or at 0, right? We can conclude that h of x, which is our composite function, as x approaches 0, is also 0. So we can say that h is continuous on the entire function line here. Alright, lastly we're going to get to what we call the intermediate value theorem. Alright, it's important because it talks about the behavior of functions on closed intervals. Okay, so the intermediate value theorem is stated as if f is continuous on a closed interval a to b, and f of a does not equal f of b. Alright, so if I plug in the two endpoints, they don't equal each other, and k is any number between f of a and f of b, then there's at least one number c in AB such that f of c equals k. Alright, so that gets kind of wordy. Let's look at an example here that might help you kind of understand what we're talking about. Alright, so the intermediate value theorem is just saying that, if we're between these 2 points on an interval, and there's a point that exists between them, that there is going to be something else of a value there that exists. It doesn't tell you what the value is, but it does tell you that it exists. Okay, so that's really what we're doing. It doesn't provide the method for finding C, but it does tell you that C does exist. Okay, that's really what it's saying. Okay, so if we take a look at it, this example might make more sense to you when we're talking about the intermediate value theorem. Okay, so if we talk about someone's height, let's say there's a girl who's 5 feet tall on her 13th birthday, and then on her 14th birthday, she is 5'7". Well, we know that somewhere between her 13th birthday and her 14th birthday, she was 5'6", or she was 5'3". Okay? We know that there is a specific point in time where she was that value. So now let's go back a couple slides. Sorry, that's the wrong direction. And look at this now. So f of a, right, that's the girl's 13th birthday. F of b is the girl's 14th birthday. So, and we know her height on her 13th birthday was what, 5 feet, and her height on her 14th birthday was 5'7". We know that somewhere in between her 13th and 14th birthday, she was 5'5". All right, that's really what f of c equals k means. There is a value there that does exist. Remember, the intermediate value theorem does not tell you how to get that value, but it says that it does exist. Okay? So let's look at it. It just guarantees the value, all right? So the intermediate value theorem guarantees the existence of at least one number c on the closed interval a to b. Okay? There's going to be more than one c, but we're just going to say that it guarantees that one does exist. Okay? So if we take a look at this graph now, we can see that what? A function that's not continuous does not necessarily exhibit the intermediate value theorem property. So a function should be continuous for us to be able to apply the intermediate value theorem. Because look here, this is what? A jump discontinuity. The left-hand limit does not equal the right-hand limit. There is a value at b, all right? It doesn't equal the value at a, but the function is not continuous. There's a jump discontinuity. So there is no value in c here, such that f of c equals k. So this is why it's very important that we understand, if we're on a closed interval or an open interval, all right, and what that really means. So when do we use the intermediate value theorem? We can use it to determine the location of zeros, or that a zero of a function does exist. Okay, we're going to do an example of that here in a second, but if f is continuous on the closed interval a to b, and f of a and f of b differ in sign, the intermediate value guarantees the existence of at least one zero. So there's a sign change, right? If f of a is negative and f of b is a positive number, there's a sign change there, which means we had to go from negative to positive, which means a 0 does exist. Or if we went the other direction, right? Say f of a was positive and f of b was negative. We went from positive to negative, meaning we had to cross the 0, all right, so that a 0 does exist. So that's where we have something good for the intermediate value theorem as it applies. And so on your homework, you're going to apply the same thing. It says use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0 to 1. So this is where we have to do what? We're really just going to substitute in the two endpoints on the interval. We're going to substitute in 0 into the function, and we're going to substitute 1 into the function. And we're going to look for a sign change. Okay, so what's going to happen? If f of a is positive and f of b is positive, there's no 0 on that interval, right? Because the sign didn't change. If f of a is negative and f of b is negative, okay, the sign didn't change, there's no 0. So we're looking for the sign to change. Okay, so if we evaluate f of 0, we get 0 cubed plus 2 times 0 minus 1, that equals negative 1. So f of 0 is negative. Then we substitute in f of 1. So 1 cubed plus 2 times 1 minus 1 is 2. So f of 1 is positive. So the function went from negative to positive. That's the exact definition for us, to be able to calculate that there is a 0 there. It doesn't say what the 0 is, right? I didn't ask you to find the 0, where it exists. All we did was prove that a 0 does exist on the interval from 0 to 1, that function crosses the x-axis. It doesn't tell us where, okay? So that's the important part about the intermediate value theorem. We just proved existence. We did not prove what the value was or where that 0 existed. But if we take a look at it graphically, okay, it looks like this. All right, so we can see what the function x cubed plus 2x minus 1 looks like. And we can see, all right, our endpoints are 0 and 1 for the x values, right, on our interval. It's a closed interval because f of 1 does, or f of 0 does exist and f of 1 does exist. So we're on a closed interval. And we know, and we calculated that, right? We calculated f of 0 to be negative 1 and f of 1 to be 2. So we went from negative to positive. So a 0 does exist. And where does it exist? At c comma 0. Remember, the intermediate value just states that it exists. It doesn't tell us what that 0 is. Okay, but that's the whole point. We are proving that something does exist there, not necessarily what it is. Okay, so intermediate value theorem, we can also use the bisection method for approximating the real zeros, similar to the other method. So, if we wanted to do bisection, so what that really means is we're going to take, remember bi means we're going to divide it in 2, okay? So if we have a and then we take a plus b and divide by 2, or we can say a plus b divided by 2 and b, all right? So we can look at the sign of f of a plus b divided by 2, and you can determine which interval contains the 0. Okay, so this one's not as common. If you want to apply it, you can, but I think, just looking at the other way, just looking for the sign change, very easy for us to use the intermediate value theorem. So, just to recap, so, how do we know if a function is continuous? Well, the value has to exist there, the limit has to exist, okay, and the limit has to equal the value, all right? So we had to remember that that's telling us that the function is continuous, okay? So very, very, very important there, and then we use the intermediate value theorem here, and we were able to evaluate the left endpoint, the right endpoint, and look for the sign change to see if a 0 existed. And then we did discuss, right, continuity on a closed interval. So as long as the, as we approach the function from the right, and it had a limit, and we approached the function from the left, and it had a limit, therefore we knew when the function was normally continuous, we knew that the function was continuous on the closed interval as well. So that's the end of this lecture. I know it's been kind of long-winded on this one. But lots of good stuff about continuity and being able to determine if a function is continuous. So make sure that you understand removable discontinuity or non-removable discontinuity and how to apply those as well. How to determine if a function is continuous on an open interval or a closed interval. Make sure you know all those rules and make sure you know how to apply the intermediate value theorem. Okay? So, like normal, email me if you have any questions, ask in class. We can go over some homework problems as well. Else, guys, have a great day, and I will talk to you soon.